I'm going to place myself as the root of the topology. So I'm going to be the root, and I'm going to do a tree with the shortest paths to every other router. And all routers do this. Okay? So in a link state, every router has a shortest path tree with itself as the route. We usually even call this a multi-routed shortest path tree, because every router makes its own shortest path tree, considering itself as the root. Sim?
Eu já tinha resposta. Eu talvez não sabia se este protocolo, o OSPF, usava mesmo o algoritmo de Dijkstra, ou se já existiam outros melhores.
No, it's the Dijkstra.
Aparentemente usa mesmo o Dijkstra.
Yeah, it's one of the ones with the lowest complexity. So, and the distance vector protocols mathematically can be described as a Bellman-Ford algorithm, but the Bellman-Ford algorithm is implemented in a distributed way, with each node propagating only in. It's not. The difference is that, so you can say why if this is more complex, why am I going to use a link state protocol? Because usually it makes better decisions because it knows the entire topology. Okay, and the other big advantage is that it's much quicker to react to failures, because in distance vectors we saw that problem in which in a failure I can go to a path that is also affected by the failure, but I don't know, because I don't know the entire topology. What I know is the distance, and I know that this one is telling me that now he has the biggest distance, so now I switch to the second best one, but the second best one in a second or two is also going to tell me that the distance is higher because it's affected by the same link. And then I go to the third, and maybe the third is also affected by the same link. So I'm trying consecutive paths, and all of them might be affected by the same failure.
Load balancing nesse caso. Se eu sei que tenho dois caminhos que estou a usar para fazer load balancing, mas não sei se eles os dois vão convergir em algum sítio, isso faz sentido estar a fazer então load balancing?
O EGRP vai fazer a mesma. As long as that rule is applied. Yeah, but in the part in where they are disjoint, they are still gonna get some advantage. But that can happen, yeah, of course. Because the only rule is that the advertisement distance is lower than the feasible distance. You have no idea what's beyond your neighbor. You just know the cost. You don't know nothing except the cost. And here you know the entire topology. So when a link fails, the information that you receive is not that the cost changed, is that the link disappeared. And you go to your topology, you prune the link, and you run Dijkstra again. So Dijkstra will only find paths that do not have the link. So it's better because of these two things. It's worse because it's more complex, and being more complex can only be applied in smaller topologies. Okay, and that's the reason why, for example, BGP, which is the exterior gateway protocol, the routing protocol of the internet, cannot be a link state because the topology is huge. Okay, the topology of the internet, even if we consider an autonomous system like a node, it's still near 1 million nodes. Okay, the internet. So a link state in a topology with 1 million nodes, forget it. Only running Dijkstra on that topology of 1 million nodes takes like, probably even in good hardware, it would take like a few seconds. At least a few seconds, probably minutes. Okay, so in a link state we have these three things, which are the neighbor tag, also known as the agency database, the topology table, which is also known as the link state database, and then the routing table, which is the forwarding database. All both these terms are equally used. Okay, you will see several times agency database or neighbor table. There isn't one that's more preferred than the other. Okay, and they are what? The neighbor table, the agency database, is the list of neighbors. The topology table or the link state database is the topology, is the description of the entire topology. And then the routing table is the result of applying Dijkstra to the link state database. Okay. So it's only the paths that make the shortest path tree from myself to every other node. Okay? So since this is, in terms of complexity, more complex than distance vector, link state protocols are hierarchical. Okay? This means what? Even inside the same autonomous system, I usually divide the network into different areas. Or in case of ISIS, which is the other very used link state protocol, here it's called areas. In ISIS, there's only two levels. There's level 1 and level 2. Okay? But there's also this hierarchy. Okay? So I can have several level 1 areas and then a level on the contrary, I can have several level 2 areas and then at least one level 1 area. Here, I need to have at least one backbone area, which is area 0, and then I can have several non-backbone areas with whatever number. Okay, so I have a special area which is called the backbone or transit area, which is area 0. And then I have normal areas, non-backbone areas, okay? And all of this inside a single autonomous system. Okay, you have here on the figure, you have this router, also receives routes from outside, for example, using BGP, or receiving static routes from an internet service provider or something. Then I have routers, backbone routers that exist only on area 0. This means what? All interfaces that belong to OSPF in this router are all in the same area, all in area 0. Then I have area border routers like R2 and R3. Actually, I have his here with the names. So I have these ones here, which are area border routers. Why? Because they have one interface on area 0 and one interface on area 1. Okay? So area border routers are routers that have interfaces on more than one area. Okay? Internal routers are routers that have all the interfaces. When I say all the interfaces that are included in OSPF. Okay? The interfaces that are not included in OSPF are not relevant for the matter. Okay, so we have these ones here are area routers because they have, this one only has an interface on area 2, no interfaces in other areas. This only has on area 1. These ones are border routers because they have interfaces on area 2 and area 0. This one is an area router but also a transit router or a backbone router because the area is the special area 0. Okay, and then this one is called an autonomous system boundary router because it has interfaces that are not on the autonomous system. This means that it has interfaces that are exchanging routing information to outside of the autonomous system using BGP, okay? Or they are connected to outside of the autonomous system and I have a static route or something. But they have interfaces that the network of, there's at least one interface here whose network does not belong to the autonomous system. And then it has another one that belongs to area 0. Of course, I can have a simpler version of OSPF, which is single area OSPF, when I only use the backbone area. I only use area 0, okay? If I have a small topology, I can do this. For example, if instead of IGRP in the first topology of your project, you can use OSPF with area 0 on all routers. routers. You don't need more than an area because you have 4 or 5 routers. Okay. Usually, you use IGRP because you already learned it, and then you use OSPF only on the second topology. But you could use OSPF also with a single area. Of course, in the second topology is the other way around. I purposely created several areas for you to have to configure it, but also in that small topology, everything could be in area 0. Okay. So this is what we already saw. I exchange link state. I exchange link states. Okay. Then I form the link state database that has the entire topology. I have agencies with this one, this one, this one, and this one. Okay. So R2, R3, R4, R5. This is the agency database or topology or neighbor table. Okay. Then I have the topology table or link state database, which is everything, the entire topology. Then I run Dijkstra, and I only stay with the shortest paths, which is the ones in red. Okay. The other ones disappear, so these ones here also disappear. Okay. And I only have this. This is the topology that stays. Okay. It's only this. This is the only topology that stays. And this is what goes to the routing table, which is the shortest path 3. So, routers form agencies, they exchange a protocol, they exchange messages. There are 5 messages, one of them is an hello, then they usually send a database message which sends the first link state advertisement of all. And then they can periodically exchange link state advertisements or link state updates. Link state updates are when failures occur. Okay, if anything changes in its interfaces, a router has to send a link state update to all its neighbors. Okay. Besides that, link state advertisements are periodically sent. Okay. So either a link state update or a link state advertisement is received, they are processed in the same way. Is this link state already in the link state database? 2 options. Yes, in that case they have a sequence number. Because since this is every neighbor sends this to every neighbor, I can receive, for example, if I have a router here, then I have some topology here. Okay, I might receive here the link state of this router from 2 different neighbors here. I can receive it from here and I can receive it from here. Okay, and it's going to be the same link state with the same sequence number, you see. Or I can even, if there's a failure here, I can receive an update that reaches me quicker through B than it reaches through C. And then I'm going to receive an update here, and then I'm going to receive the same one here, but the sequence number is the same. Okay, so I'm going to ignore it. So if the sequence number is the same, I'm going to ignore it. If it is not, I'm going to see if it is higher. Okay, if it's higher, it's the same thing as if it's not in the database already. If it is lower, it means that it is already deprecated. So I am going to send a link state update with my information which is newer. Okay? If I receive a link state update with a sequence number lower than the one that I have for that link state, I'm going to send back to the neighbor my version which is fresher and newer. So if I do not have it, or if it has a higher sequence number, meaning that it's more recent, then I'm going to add it to the database to build the topology. I'm going to acknowledge that I have received it, and I'm going to send it to my other neighbors. Okay, so I receive this from one neighbor and I send to every other neighbor. Since this is done, this is why I need to have the sequence number, because this is flooded to everybody except the one that I received. I need to stop this if I start receiving the same information repeated, and I know that because I receive another LSA or LSU with the same sequence number, so I know that I need to ignore it to stop the flooding process. Okay, so after I have added the link state to my topology, I have to run Dijkstra again to calculate the new routing table. So every time a new link state arrives, this means that a new link appeared or a link disappeared, one or more. This means that the topology is different. This means that I have to recalculate the paths. Okay, so every OSPF announces a link state advertisement for the interfaces that it owns in that area. Another thing, link state advertisements are sent to that area only. So if I have an interface on area 1, I'm just going to send that information of that link to neighbors on area 1. Okay? And I'm going to send them to a neighbor on area 0, but not, for example, for a neighbor in area 3. Okay, this is important here. If you have one here, for example here, in that here, information of this link, imagine that I have a link here, okay, which is on area 2. This one here is on area 2 also, okay. This link is not sent to here. So the link state advertisement that contains this link is not sent to here. It's sent to the ones that are in area 1, and then the border router sends to the backbone. This router will learn that this link exists, but it will learn through area 0. This is why it is also called the transit area. Okay? So this means that even if this link exists here, R6 is only going to find about this network when it receives via area 0. Okay? It is not sent to other areas. So a link state advertisement, a link in an area is only sent to neighbors of that area and to area 0. Okay? So you can see show IP OSPF database. Okay, show IP OSPF database then shows you information about the link states that you have received. You see in this case from area 1, and this is the information of the link. You see, it's an ID of a link and the router that announced it. Okay. So OSPF does what? It needs to discover neighbors and form agencies, flood the LSAs and LSUs to build the link state database, and then compute the shortest path using Dijkstra, and then install the resulting routes in the forwarding table. Okay? Then I need to detect any changes that happen and propagate those changes. Okay? So at the beginning, when I do the neighboring, I send the first advertisement, and then when there is a change, I also send it. So we have DLO, which is used for in the beginning to form the agency. Then we have the first link state, which is called database description, and then routers can request link states, okay, and receive updates. Updates are sent when there are failures, and routers can also request an updated version of the database description with this message link state request. All these messages are acknowledged with this link state acknowledgement message. Okay? Now, this exchange of link states has some implications, okay? When I only have one link connecting two routers, okay, what we have shown is that this is a network and this is another network, okay? So I send my link states here, no problem, send my link states, send my link states, send my link states. This usually happens in either serial interfaces, which are not Ethernet interfaces. There are other protocols that are used for connecting two routers, okay, because Ethernet is supposed to be broadcast, okay? It has the FFF address, the ARP, and all that. So usually there was a lot of back in a few years when Ethernet was not so cheap. Ethernet was more of a local and broadcast technology, and routers were connected using other layer 2 protocols like HDLC, which is kind of being phased out, and point-to-point protocol. Point-to-point protocol still exists. Why? Because it can actually be used on an Ethernet cable. Okay? In that case, it's called PPP over Ethernet. Okay? When we use this, the physical layer is the same as Ethernet, same cabling, same representation of bits, all that, but this does not use carrier sense multiple access as Ethernet because it's not broadcast, it's only a point-to-point link. Okay? Another thing that can happen is that even if it's not PPP over Ethernet, I can have two routers connected by an Ethernet interface, which is what happens in our lab. Okay? So using regular Ethernet, but I only have two hosts on this broadcast domain. So this is a case where the broadcast domain is only these two hosts. Okay, this is an Ethernet, but it only has 2 points on the broadcast domain. So either if I'm using a serial interface with point-to-point protocol, HDLC, or I'm using Ethernet with point-to-point over Ethernet, or Ethernet but without a switch here, so with only two hosts, or with only two endpoints. This means that I don't need to do, I have OSPF point-to-point, okay? This means what? In OSPF point-to-point, I only have a neighbor on that segment, okay? But in Ethernet, I might have, for example, a switch here. This represents a switch, okay? I can have a switch here. If you want the traditional design, I could have this like this. 5 routers, and these 5 routers are connected using a switch. Okay? This is entirely possible. This means what? This interface, this interface, this interface, this interface, and this interface are all in the same IP subnet. Okay? Are all in the same network. This means that this router has, through this link, not one, but 1, 2, 3, 4 neighbors. And it would be inefficient to send link states to everybody. Okay? I can do that, but it's a waste of bandwidth. Okay? Because I'm going to send, the first time I send a link state here, if I send this with a multicast address or a broadcast address in Ethernet, this will arrive to everybody. So there's no point on sending 4 different link states instead of just one. Okay? So what is done is this. I can use what's called broadcast OSPF, and in broadcast OSPF I elect a designated router on the segment and a backup, but this is just in case of failure of this one. Okay, so I select a designated router, and what is done is that I send link state advertisements only to the designated router, and then the designated router does a broadcast to everybody. Okay? This is just purely to save on the number of messages that I'm sending here, taking advantage of having a broadcast network here, which is Ethernet. Okay? So what happens is, usually without configuring anything, by default, the Cisco routers check the type of the interface, and if the type of the interface is Ethernet or fast Ethernet or gigabit Ethernet, they are going to be on broadcast. So they are going to elect a designated router, which makes no sense when I have only this, which happens, for example, in your lab, because you are using gigabit Ethernet interfaces. So it's going to elect a designated router and a backup designated router, which has no point, because one will be the DR and the other one will be the backup designated router. And in this case, this doesn't do anything, okay? Because this is going to send the LSU here, and this one is going to send the LSU here. They don't have anybody else to send the messages to. So you should configure all Ethernet interfaces that are just directly connected to another router, like an OSPF point-to-point type interface, so that no DR and BDR are elected. If they are connected via switch and there is more than one neighbor accessible through that interface, then you should leave it at broadcast, in broadcast mode, and it will elect a designated router and a backup designated router to disseminate the information through using always the designated router. Okay? How is the election done? The designated router is the router with the highest OSPF priority. OSPF priority is configured in the interface. Okay, so if I want, because this is only relevant for the interfaces that are on a broadcast segment. Okay, if I have other interfaces here, this is not relevant for these interfaces. Okay, it's only relevant for this one here. So I need to configure the priority in the configuration of this interface. Okay, the default priority is 1. So you just need to go to the router that you want to be the designated router, go to the interface that is connected on the segment that has the switch, or if you want for some reason to have a designated router, even if it's point-to-point, it doesn't make a lot of sense, but it might be just to force you to do the configuration. And you configure with a priority higher than 1. Okay? In this example here, okay, the number 3, the priority 3, so the default priority is 1, so this router will be the designated router. Okay, and this is the mechanism. Okay, there's a link state change. I send the link state update to the designated router, and then the designated router sends them back to the other neighbors. Okay, so all communication is done through the designated router, and then the designated router uses a multicast address so that everybody in the segment will open that message. Okay, so configuration, we have seen everything. Link state protocols, exchange link state information, build a topology, run Dijkstra. I can have more than one neighbor in a link if that link is connected to a switch, to a LAN. Okay? If I have more than one neighbor in that link, I need to elect a designated router and a backup designated router, so that I don't waste bandwidth sending link state updates that everybody's gonna get. Okay? More than once. So configuring. So we will have routers that have single area configuration. This means what? All interfaces are on the same area. I'm going to have routers where some interfaces are in one area, other interfaces are in another area, okay, multi-area configuration. I need, same thing as in IEGRP, I need to decide the networks that I want to have. I need to look at the topology and try to have contiguous subnets on places where I can summarize. Okay, so I have to see if I have points where I can summarize routes. All the routes below that point should be contiguous so that I can make a bigger prefix for the summary. I need to define the areas so that I know which interfaces are in which areas. Okay, and then I'm ready to start configuring. Okay, so defining the address so that I can summarize, okay, in the summarization and redistribution points, which are points of the topology that where the topology strangulates. Okay, so where you have a place where a whole part of the network can only be accessible by one or two routers. Okay, decide where the areas are, and then I'm going to start implementing. Okay, so OSPF configuration, similar to IEGRP except for the areas. Okay, so router, in this case OSPF, and in this case this is not an AS number. So in IEGRP this number had to be the same in all routers. In OSPF, no, it's local to the router. Okay, here, for example, we are using two different numbers. There's no problem. This is local to the router because I can have more than one instance of OSPF running. Okay, and if I have, for example, two instances, the interfaces that belong to an instance will only do agencies, will only send link state advertisements of links that belong to that instance through neighbors that belong to that instance. But usually we don't have more than one. Okay, but this number here does not have to be equal. So router OSPF, this is the process ID, and then I have the network command. In this case, this is the same as it was in IEGRP, meaning what? It serves two purposes. It's a rule to see which interfaces belong or not to OSPF. Okay, and in this case, not only belong or not to OSPF, but to which area. Okay, so in this case I need to add the area. So this means what? That all interfaces that start with 10, in this case, because I have a 10.0.0.0.0 to 155, 155, 155. So everything that starts with a 10 belongs to area 0. So this means what? It is in OSPF, so I will try to do a neighboring via those links, and those links will be announced in a link state advertisement as being in area 0, meaning that they are going to be advertised to routers of area 0 and to all others, because area 0 is the transit network. It announces to all areas. Okay? In the case of R2, okay, so this is R1, which is only on area 0, and it has this interface here. Let's imagine that this is a /24. So the network that's going to be announced in the link state is the network of the interface. So it's going to announce the 1064, sorry, not 54. The 1064.0.0. This is the network that's going to be announced, not with the cost, because this is not a distance vector, but this is the network that the router will say that it has directly connected to it. Okay? Why? Because there is an interface with this address and this mask, and this interface starts with 10. which is on the rule. Okay? If there was here a 10.34.0, another interface, 31.0.1/24, then the 10.31.0.0 would also be announced. Okay? And not the 10.0.0.0/8, which is sometimes the mistake that you do, because you look at this and think that this is to announce the network. This is not to announce the network, this is to create the rule to match with the interfaces. The networks that are announced are the ones of the interfaces. Okay? No, because you don't need to put the /24. This is not a /24. This is a wildcard mask. This is only a rule. What you need to think here is, it has to match everything that I want to include and leave out everything that I do not want to include. In this case, I want to include everything that starts with a 10. If I had these two networks and I wanted to include this one but not this one, then this wouldn't work. In that case, I would have to do a network 10.64.0.0, 0.0, 255. Once again, I don't place a 0 here. Why? Because there's nothing starting with 10.64 that I do not want to include, so I don't need to be more specific than that. Okay? So this has nothing to do with the /24. The /24 is what exists on the interface. Think of this as a rule. Okay? This is why it is a wildcard mask. It's a rule for matching. Okay? So you can make it as simple as possible. The only thing that you need to assure is that it won't include anything that you don't want to belong. Okay? So in this case, since there isn't anything starting with 10 that I do not wish to include, I can be as simple as this. Okay? If there were more interfaces starting with 10 that I do not want to include, or that I want to include but in a different area, for example, this down one could be on area 3, then I would have to do this separately. Then I would have to do this first one with this mask here for area 0, and then I would have to do one to the other one with 10.31. Also, no point on placing the 0 here with the 0 here, because there is nothing starting with 10.31 that isn't on area 3, and I just need to do this again. Yes, but it has nothing to do with the mask of the interface. You place a 0 here if you want this to be 0. In this case, I don't care, because I don't have anything starting with 10.64 that I do not want to include. So I don't need to go to that octet. I don't need to force that octet to be 0. It could be anything. This means that without the 0 here, if I have a 10.64.1, it will also enter on door 2 or door 3 or whatever. And then the network that's going to be announced is whatever network is there. If it is a /27, it will be a /27. If it is a /24, it will be a /24. If it is a /30, it's /30. Okay, so this is just to say if it belongs or not to OSPF, and in OSPF, since we have areas, to a specific area of OSPF. Okay. So here we have two areas, you see. So in this case, we have one interface that starts with 10, that is on area 0, and another interface that also starts with 10 on area 1. So in this case, I can no longer use this, you see. In this case, I cannot have 10.0.0.0.0 because in this case I have something starting with 10 that I do not want to be in area 0. Okay, that is the reason why this network command is different from this one, because in R1 there is nothing starting with 10 that does not belong to area 0, but here there is this interface here that starts with 10, sorry, this one that starts with 10, and it's on area 1, not on area 0. Okay, and this is another way that you can do this. You can come to the interface itself and configure, but I'm going to show you the network command here for the other one, which is 10.2. You could do this, for example. Also, you see here, in this case, this is all with zeros, meaning that only an interface exactly with that IP will belong. But this is not needed. I could also have done this with a 0 here and a 0 here, and a 255 here and a 255 here. It also works. Okay? Because there is nothing starting with 10.64 that I do not want in area 0. So it could be like it is, it could be like this. And also, instead of configure this in the interface, I could have another network command here. This would be for area 1. Area 1. Okay, another way, which usually you don't do in the projects, but you could do also, because it's more, it gives more work. Okay, instead of using the network command to make a rule and then the interfaces that match the rule belong, you can go and say interface by interface if it belongs or not and to which area. But this is more work, okay? If you have 10 interfaces, you have to go and do this command in all of the interfaces, placing them in OSPF and in the respective areas. And if all those 10, for example, belong to the same area and start with the same number, you just need to do one network command instead of going into all of the 10 interfaces and doing that command in all of the 10 interfaces. Okay, but both are possible. There are two ways. So in this case, I'm not using a network command, so I wouldn't need this network command down here, because for this interface I'm going in the interface configuration and I'm going to say that it belongs to OSPF area 1. So you have the two possibilities. Another thing that you should do when you configure router OSPF is use the command router ID. You don't need to, but it's good. Why? Because otherwise, the router ID is what? Is the identification of the router in the OSPF process. For example, when you do a show IP neighbor, show IP OSPF neighbors command, it will show the neighbors that you have in OSPF. How are they identified? What appears there is what's called the router ID. The router ID is an IP address, but you have to be careful. It has the format of an IP address, but it's not an IP address. Okay? It's just an identification of the router. If we don't configure it explicitly, it will be the highest IP address that the router has. Okay, it does not have anything. It might even be a router that it might even be an IP address that it isn't even on OSPF. Okay, included on OSPF, because it's just an identifier. Okay. So it's the highest IP address on an active interface at the moment the OSPF process begins. If I only have physical interfaces, I might have what's called a loopback interface. A loopback interface is used in routing for several things. It's configured like this. Okay, interface, loopback, and then I give a number. I can have lots of them, okay? And then I give it an IP address. So this is an interface that isn't physical, okay? It's like the 127.0.0.1 in computers, okay? So it's an IP of your machine itself that can be reached without leaving the machine, okay? But you can create it in whatever, and Cisco actually allows you to do this, although this is not compliant with the IP standard, IPv4 standard, because this is a /32 mask, which does not exist in IP. But for a loopback address, they allow to use it because this is a special interface that only has a network that only has one point. Okay, so it will never use broadcast, so it does not need a broadcast address. And the IP can serve as simultaneous the host address and the network address. Okay, but most of the time we use this with a mask, a /24 or a /30. Most of the time, if you should use a /30 here, which is the biggest mask that complies with the standard of IP, meaning that it has a network address, two hosts address, and a broadcast address. Okay, so if a loopback address exists, then it's the highest IP, but of the loopbacks. Why? Because a physical interface can go down. Okay, for example, if the link is cut, okay, or the port is disconnected. And if the link goes down, that IP ceases to exist. Okay? And this would mean that the router ID would have to be recalculated. Okay? And the OSPF process would have to start again. It will have to do another neighboring because its identifier changed. Okay? So if there is at least one loopback, the router ID will be the highest IP address of the loopback interfaces. Why? Because loopbacks are never down unless the entire router is down. But if the entire router is down, also there's no restarting of OSPF nor anything else because it's all down. Okay? Okay, so this is you will see this, for example, on BGP. It's very important on BGP to use loopback addresses to do neighborings because of the same reason. Because you do a neighboring, and if the link goes down, you lose the neighboring. But if you have the neighboring with the loopback interface, you can still. But this is in BGP. Why? Because in BGP I can have neighborings to routers that are not directly connected to me. On OSPF and EGRP, that doesn't make sense. I only have neighborings with routers that are directly connected to me. Why? Because I do not know how to reach other routers. Okay? I only know how to reach other routers after I do the neighboring. Okay? So it's the chicken and the egg. I cannot have a neighboring with a router that is not directly connected to me because I never know how to reach other routers without the routing protocol. In BGP that's not true. Why? Because BGP it's an exterior gateway protocol. So I can have neighborings that can span multiple routers, provided that the routers know how to reach the endpoint, and routers can know how to reach the endpoint because I can have an interior gateway protocol running. Okay. So, but for now, loopbacks are for this. Two main uses. In routing scenarios, when we are trying to see if the configuration is working correctly, even in operators, in real operators, we go to a lab or we use a tool like CML, like you are using, or Packet Tracer, or GNS3, which is another tool. All those are used in real life to check if a configuration will be good in a scenario, in a network that I'm assembling. So, and in these cases, when I'm just trying to see if this routing configuration will work or not, I use a loopback address to simulate, for example, a VLAN subnet, okay? Because if this loopback is included on OSPF or on IGRP or whatever, this network will be announced, okay? And it for the routing purposes is the same thing as if I had here a physical interface connected to a switch in a VLAN and had a subnet there. Okay? So I can have these two situations, you see here. I can have advertised loopback addresses, for example, to simulate networks, to see if the routing is working. Or I can have loopback addresses that are not advertised, okay? Also, another thing is that I can ping. If I advertise this address, I can ping and use these addresses also to test connectivity, to test if the routes are being sent and if I can reach one router that is distant from me, if I can reach it or not. Okay, so the best way in terms of router ID is not to rely on the selection of the highest IP address. The better way is to configure it like this. And this is not an IP, this is just, it only has the format of an IP. There's actually a rule that people usually follow, which is, if I give a name to my router, for example, router 1, then I come here and I use 1.1.1.1. Okay, why? Because if I'm troubleshooting and I go to a router and I do show IP OSPF neighbors, I look and I see 1.1.1. I look at the diagram and I know immediately, oh, this is router 1. It's working good. I have an agency with router 1. Okay, so this is a good idea to configure, and you can even use here an IP address. It is not an IP address, but you can use something that helps you identify the router when you're troubleshooting. For example, for router 1, people sometimes use this. For router 2, use 2.2.2.2. For router 3, 3.3.3.3. Whatever, okay? So it's a 32-bit number, but it's not an IP address, okay? Why is it a 32-bit number? So that if people don't configure it, they can use the highest IP address for them. It's the only reason it has the format of an IP. Okay. If you change this and you already have OSPF running, it will only take effect if you restart the OSPF process. Okay. But if you do this in the router configuration, then the next time when it starts, it will have that ID. Okay, so if you do show IP OSPF, you have the process that it's running and the router ID here of this router, the number of areas that it has, how much are normal, how much, these are special types, we're not going to see it. The difference is only that this type of areas sometimes summarize link state advertisements from other areas that they receive through area 0. Okay, so this is the configuration we already saw. We need to see if the routing protocol is working. You can do show IP OSPF. Usually the quickest way is to go and see the routing table and if routes are appearing there. Routes learned via OSPF. If they are there, you don't need to do these steps in the middle. These are things that we usually just do when something is not working, because otherwise we just do show IP route and see if we have OSPF routes there already or not. This takes a little while. IGRP also takes a little while. A few, maybe 1 or 2 or 3 seconds to do the hellos, build the agency the first time. Then if a link goes down, it's quick, it's milliseconds. But to form the agencies in the beginning, it takes a little while. BGP is worse. When it's BGP, it takes really a couple of seconds. Okay, so this one here is show the neighbors. You see here the neighbors with the IDs. You can use with the detail. It says which interface is connected to which of the neighbors. Okay, if things are not appearing on the IP route, then you have to start doing this. You have to see if you have the neighbors. If you don't have the neighbors, maybe to go see if the links are up. The links might be down, and that's why it's not making the neighborings. Or if you configure the network commands correctly to include those interfaces. Otherwise, if you don't include the interfaces, you won't have a neighboring via that interface. Okay, and then finally show IP route. Here in this case, show IP route OSPF only shows the OSPF routes. If you don't put the OSPF, you will see the OSPF routes and the directly connected routes and other routes if you have other protocols. For now in your project you don't have, in the second scenario you only have OSPF, and in the first scenario you also only have either IGRP or OSPF. You can also do show IP protocol, and then it's going to tell you the routing protocols that are running. Okay. Oh, this is something that we already saw in IGRP, which is sometimes I want to include the interface because I want to announce in my link state advertisement that I have that link, but I do not want to exchange hellos or do neighborings via those links because there are no routers there. Okay? This is the case here. So this is representing, for example, a VLAN. So the only thing that exists here are switches and hosts, no routers. But I need to tell the other routers that I have this network connected to me. So this interface must match with a network command, or I must go to the interface and do the router OSPF ID area command to tell that this interface belongs. But if this interface matches a network command, or if I go to the interface and say that it belongs to OSPF, he will also try to do an agency through this link, not just announce that it exists, which is what we want, but he will also try to make an agency through here, which I don't want. So this is exactly the same thing that we do in IGRP in this situation, which is I can use the passive interface and say which interface I want to be passive, or, for example, here in R1, I have 3 interfaces that I want to include on OSPF, but that do not form neighborings, and only one that is included on OSPF and forms neighborings. So in this case, it's better to do it the other way around, which is to do the passive interface default, which makes all interfaces passive, and then just say that this one here is no passive interface. So this depends. By default, they are all active, and you go and do passive interface on the ones that you don't want to make neighborings. If you have a situation like this, where you have more interfaces that are supposed to be passive than you have active, you can use the passive interface default, and then the no passive interface for the ones that are active. Being active interfaces that form agencies with neighbors. So the cost is basically connected with the bandwidth. Okay, so it's 10 to the power 7 divided by the bandwidth, and Dijkstra chooses the paths with the least cost. Okay. Usually it matches the geodesic shortest path, meaning that the path with the shortest number of hops, but that might not happen if the links have a big difference on bandwidth values. I can have a path with one link with a very poor bandwidth that has a higher cost than another one with two links, but that each link has a much better bandwidth. Okay. Usually in modern networks, it's not the case because links have at most 2 or 3 types of bandwidth. Okay. You can try to change this. Actually, there's a lot of research because Dijkstra calculates the shortest paths according to the cost. Doing the routing in an optimal way is very difficult because in a topology, everybody is using the shortest paths and it has to be like that. Otherwise, I would have forwarding loops. But usually the network starts to become congested when I still have available links. Okay, usually networks are underutilized when they start having congestion problems. Why? Because these protocols do not allow me to explore all the diversity of the topology because I'm always choosing the shortest ones. Okay, there's actually an algorithm that you can use given a topology to choose the set of links that will more quickly saturate one link of the topology. Because you can calculate something that is called the centrality of a link, which is the number of shortest paths that it belongs to, roughly. Okay, and the links that have high centralities are links that belong to a lot of shortest paths, and those are the links that get congested first. And most of the time, there will be alternative paths to do that. So all this to say, what you can try and meddle with the cost of the links. Okay, you can go there and do a bandwidth command. And you might say, why or hell there exists this command? Because there are attempts of trying to solve this as an optimization problem, in which what I do is I try to change the costs of the links so that Dijkstra gives me paths that divide the load better. But this is NP complete and it's unsolvable. So usually it can only be done with simplifications. And it's a well-known problem that is unsolvable. Okay, so what's left here to see? Same thing that happened on IGRP and that we have to consider on all routing protocols. Summarization and default routes. Remember? Both of them have a clear goal, which is to have routing tables as small as possible, because the matching process on IP is very intensive, because I cannot stop on the first hit. I need to see if there is a longest prefix match. Okay? And another thing is when I have failures, if I have summaries, there's parts of the network that do not need to know, okay, that something failed, because they only know the big subnet and they don't need to know if the smaller subnet still exists or not, because it doesn't make a difference. If it does not exist, it's not reachable. Okay, but the other ones still are, and I don't need to know that the other one, that one disappeared. Okay, so this reduces having summaries. In linked states is even more. It's even more important. Why? Because I have less information on the topology. Okay, so less complexity. When I do a summary, for example here, I'm going to summarize these two networks in just one. This means what? Imagine that there is another router here. For this router, the topology is only this. The topology is like this. Okay? This router does not know that all this exists. The only thing that it knows is that it has here a network, and that network is the network that includes these two. Okay? So if, for example, this link fails, he does not know, he doesn't even know that this link exists. Okay? This has several advantages. Longest prefix match is quicker because the table is shorter. Calculation of Dijkstra is quicker because the topology is simpler. And it does not make a difference. Why? Because he always has to go through this route. So there's no point, for example, imagine that this route there are two networks here. There is no point on this router calculating these two different paths if it always has to go here. It might calculate only this one, which is much quicker, provided that this network here includes this and this. If this network here includes these two, I only need to know these three. I don't need to know that there are these two branches. Okay? I don't need to know that there are these two branches because I'm always going to forward the traffic to this router. Okay? So this is another big advantage that in distance vector was not so relevant, but here it's a lot relevant because the summarization not only diminishes the routing table, but also diminishes the link state database. Okay, of routers that are behind the point of summarization. Okay, routers that are behind the point of summarization do not know the specifics of the topologies. They do not need to know. For them, that is just a stub with the big prefix. Okay, and Dijkstra is going to run faster and all that.
Are areas always summarized, or areas?
No, not automatically. Not automatically. No, you have to configure. Okay. What there are, we're not going to see here, is special type of areas that, for example, do not know the specifics of other areas. They replace all by a default route. For example, there is one called the not so stubby area, which is something like this. Imagine that you have an area here that only has a point for area 0, for example. This only has a point for area 0, and there are other areas here connected to area 0. Okay, so there's no point on knowing which networks exist here, which networks exist between areas. I do not know the specifics of the routers, but I know all networks. Meaning what? For example, without summarization, in this more simple case we have here, in this case here, I would know this. If I had this router here, this third router here, for this router here, the topology would be this, and I do not know about these 4 routers, never, even without summarization, because they are in a different area. But I know that there are 2 networks here. So this is the topology that he sees without summarization. This is the topology that he sees with summarization. He sees only 1 network. But he never sees that these 2 routers exist, because they are in a different area. Okay? Between areas, the only thing that is sent is all the networks that exist in that area are seen as connected to my border router. Okay, so any network that exists on area 1 for routers in area 0 will be seen. Actually, area 0 is a bad example because area 0 sees everything because it's a transit network. But if I had here area 2, okay, area 0 only propagates to area 2, Only propagates the networks, not the topology, not all the topology. So area 2 only knows that the topology of area 0, and then the networks of area 1 for area 0 are directly connected here. Okay. Why? Because he only needs to know the path until here. From here on, this one will know, and this one will choose the shortest one, you see. Because each router only decides the next hop. So there's no point on this one calculating the shortest path through here if it always has to go through here. Okay? And the only thing relevant is if it's going here or if it's going here, for example. Because routers, remember, and this is called hop by hop forwarding. So each router only defines the next one, not the entire path. So there's points when I can have summarization, where I can have default routes, because I only have one shot, I only have one hypothesis for the next hop. So there's no point on using processing power to calculate Dijkstra with the entire topology. You see, I can look at the topology as if it's just all networks connected to that router. In this case, for example, imagine that you have this here and you have a lot of areas here and all that. For this router here, he only needs to know this, because he only has one hypothesis. So for it can be like all networks are connected to its neighbor. He does not need to know that they are not directly connected to its neighbor. And this is what happens with the areas. That's why areas exist. Areas exist exactly for that, so that the router does not need to know the entire topology. Okay, for scalability reasons. So the summarization is done like what? In IGRP, it was in the interface. For example, if I wanted to announce summaries, it will be in this interface here, or this one and this one and this one. All interfaces that would announce things here, I would need to go to their configuration and say that I wanted to announce a summary through those interfaces. Here, no, it's by area, okay? So it's done inside of the configuration of the router, not in the interfaces. And how is it done? I say that all area 1 is to be included in this range. Okay, so this is a /27, which are blocks of 32. So this goes from 64 to 64 plus 32, okay, which is 96. And this includes both of these ones, okay? Actually, that includes everything from 192, 168.10.64 to 192, 168.10.96. So all IPs in this area are included in that prefix, and this includes these two networks. Once again, for example, this here, I left this here on purpose. These two interfaces are to belong to OSPF, but both of them are on area 1, right? And the only other interface that I have starts with 10. So this is not needed. I could have done this just like this. I could have actually done it like this even. Okay. Area 1. Okay, I could have done just this network. I don't need to do both of them. Okay. Why? Because there isn't nothing starting with 192 that I do not want to include in area 1. Okay? Because the only other interface that I have starts with 10. The one that is on area 0. I could have done it like this. I could have done it with a 0 here, and here with the 168. If, for example, I had 192.168.20 that was on area 0, okay, and so on, okay.
We could have had a smaller mask in the range.
There's no point on doing this, which means you have to calculate the wildcard mask, which is the inverse of the /30, but it's not needed, okay? It's unnecessary work.
No, when you do area 1 range, when you summarize,
Yes.
it would have been higher than 27.
Probably because you don't need to reach 96. Yeah, you could use a /28, which is 16 in 16, and it will be all. Actually, this is 16 in 16. 8. You could use 8 because this is 4. So you could use a /29 here. You could have used a /29. A /29 would go from 192, 168, 10, 64 to 64 plus 8, okay, which is 82, okay, to 82. You have to see if this is a multiple of 8 also. It might not be the case. This might not be 64. You would have to see going in blocks of 8, 0, 8, 16, 22, 20, 30, 38, 38 plus 8, 46, 46, 52, 52 plus 8, 60. It has to be 60 here, okay, not 64. If you use that one, if you use /29 here, it would have to be 60 here, okay? Because then you have it on 68, and it's not good because then you have it's from 60 to 68, and 68 is not included. Okay, so in this case, this will not be included. So this is 29 cannot be. 28 we will have to do the same exercise and see if it can be or not. But you have to be careful with that. Because although you need here only a block of 2, you have to see if it's a multiple of the block that you use. If it fits. Okay? So, to end, we just need the default routes. Okay, this is just another exercise, or another example. Okay, in this case you have blocks of 22 here, of 32, but in this octet, okay, in this octet here. Okay, so this goes from 64 to 64 plus 32, and this one goes from 96 to 96 plus 32. Okay, and this will include what we want. 96 plus 32 goes to 96 to 127, and here 64 plus 32 goes from 64 to 95. Okay, in this case, summaries for both sides. I have a summary for area 0 and another one for area 1. Okay, so all area 0, when it's announced here, will be with this prefix, and all area 1, when it's announced here, will be announced with only this prefix. Okay. When I have summaries, I have a special type of link state advertisement, okay, which is this type 3 summary. Then default routes. So same thing as in IGRP. Sometimes usually this happens to outside, okay? So outside of my autonomous system, to go to the internet, okay? To go outside of my network. There's something that I could have BGP here. I can have some routes that are announced by BGP via the service providers. Not all of the internet, that's very rare, because that's a lot of prefix, but sometimes ISPs announce via BGP their networks, just them, not the entire internet, just them. Their networks and the default network. Okay? Or sometimes only the default network. Okay? But if I don't have a routing protocol here, I need to announce a default route inside, so that everything that I do not learn through OSPF, meaning what? Everything that's not on my network, that's outside of my network, goes here or here. In this case, I have 2 exit points. I have 2 default routes. Okay? I configure this router to announce one, and this router to announce another one. Okay? This on OSPF is very simple. It's inside of the routing configuration. You just use the command default information originate. If you want to place a metric, you can place a metric. Otherwise, you can use the always phrase there if you only have one. If only one router has a default route, instead of placing a metric there, you just do default information originate always. Of course, the default route must exist, because only with this the routers will announce a 00000, but then packets will reach R1 or R2 and they do not know where to send them. Okay, that's why we have this here. This address would be the address of this interface. This address would be the address of this interface. Okay, actually not these ones, the ones on the router. Okay, this means what? So with what's in orange, they will announce the link 0000000, because this is a link state. They do not announce routes, they announce links. So they will tell the other ones that they have a link 0000000. So the other ones, when the packets does not match anything else, it goes to that router that has the 0000. So when it arrives here or here, he must know where to send it. That's why they have the default routes here. But for example, in your project, you don't need to create the route, because the only thing you want to have is the default route, and actually there is no connection outside, so we don't even have a link to give us the next hop. So, and just the final thing is a problem that we might have, which is when routers are not connected to, when not all areas are connected to the backbone area. Okay, so we have shown that link states from area 1 go through the backbone to other areas, even if there was a link here. Okay, so if an area is discontiguous from area 0, nobody will know any networks from that area. Okay, also the area 0 must be contiguous. Okay, we'll see here problems. For example, in this case, we have the more common case, which is I have an area, which is area 20, that has no router on area 0. So this is a problem. Why? Because this border router here cannot announce these networks, or this topology cannot be announced to either of these neighbors. Okay? Why? Because link states from an area are only sent to area 0, okay? Not to other areas. So this border router here does not send link state advertisements from area 20 to here nor to here, okay? This means what? This means that nobody knows nothing about area 20. Okay? If you go and see a routing table here, you won't see any networks off here. Why? Because nobody knows that it exists. Why? Because this border router does not announce to area 10 the things of area 20. Okay? And area 20 also does not know anything about anybody else, because border router 1 also does not flood link states from area 10 to area 20. So this also does not happen. So it is disconnected from everybody else. Now imagine that physically I might not be able to put a link here to a router of area 0. For example, this one here. This physically might not be possible to make. What I need here is an interface on area 0. Okay? If this router here had an interface on area 0, just one, I had my problem solved, because he would send the link state advertisements through that interface to area 0. But it does not have. So one possibility would be to connect a physical interface in area 0. So this IP would have to belong to OSPF area 0. And then this would have to connect, for example, here in an interface that also belongs to area 0, or in one of those. If this is not possible, I can make a virtual link. Okay? A virtual link is what? I go here and I configure a virtual link using the router IDs. Remember the router IDs? In this case, they were explicitly configured. 1.1.1.1, 2.2.2.2. If they were not, they would be the highest IP of these routers. So I go here and I say that I want to make a virtual link to this router with this router ID, traversing area 10 that this router knows about, because he has these interfaces on area 10. This makes what? By configuring this virtual link, it's like I'm making an interface appear here that belongs to area 0, and I have the problem solved. Okay? So this is exactly the same thing as if I had connected a physical interface. Okay? And now he knows that he can send LSAs through here, and this is kind of a tunnel, and it will go to area 0, and then area 0 will send them back to area 10. Okay? This could also be used to solve a problem of discontiguous area zeros. This is more uncommon. This could happen, that is the example here, if two companies merge. I don't have a direct link between them, and I want to place all the routing on two different offices together or something, and I only have a connection here which is on a different area. It's the same thing. I do a virtual link from this one to this one using the router IDs, and this makes an interface of area 0 appears here, and another of area 0 also appear here, and it's like it's all merged. Okay, but usually this problem is more common. Okay, so I need to make a virtual link traversing the area to make an interface of area 0 appear there. How is this configured? Very simple. I go here and I say area 1, which is the area that I'm going to traverse, virtual link, and then the router ID of the endpoint. In this case, is this the router ID? Okay. Why? Because somebody configured it, because otherwise it would be 172, because this is higher. But somebody configured this as a router ID, and here the same thing, because otherwise it would be this link that had the highest IP address, and it would be this link that would be the router ID. And in the other side, the same thing. Area 1, the area that is being traversed, virtual link, and the router ID of the other part. Okay? You can check with show IP OSPF virtual links if they are up. Okay, and if you see show up IP OSPF database, you will see a new neighboring being formed there. Okay, that's it. Right on time.